Welcome to a new session. Today's concept is refraction through spherical surface. In this class, we will see what is meant by spherical refracting surface, what are sign conventions used in spherical refracting surface, along with what is the relation between object distance, image distance, radius of curvature, and refractive index of the given medium. That we will see. Before that, we should know what is meant by spherical refracting surface. See here, the spherical refracting surface is a curved surface in which it forms a part of sphere. The part of sphere which form the curved surface, that we are calling spherical refracting surface. Generally, how spherical refracting surface looks like, that we will see. See here, I can call this is one spherical refracting surface. This is one spherical refracting surface. Simply, this one becomes spherical refracting surface. See here, this I can call. This one I can call spherical refracting surface. How it is? The spherical refracting surface is a refracting medium in which its curved surface becomes part of sphere. One more surface looks like. Look at it. I can take this is one type of surface. Right around this, or it becomes like this. Shall I take this? It becomes like this. Right here. This refracting surface in which its curved part becomes a part of sphere, that we are calling spherical refracting surface. Here, two types of spherical refracting surface available. One we are calling convex spherical refracting surface, and second one is concave spherical refracting surface. See here, this I can call convex spherical refracting surface, and this one we are calling concave spherical refracting surface. Very simple. See here, this one I can call Rarer medium, this one I can call Rarer medium, and what about this one? This I can call denser medium. Similarly, this I can call denser medium, and what about this part? This part I can call Rarer medium. Right around this, we know the meaning of denser and rarer. The medium which has low refractive index called as rarer medium, and the medium which has a high refractive index called as denser medium. See here, I said two types of spherical refracting surface available. One I can call convex spherical refracting surface. Convex spherical refracting surface. Convex spherical refracting surface. Second one, this I can call concave spherical refracting surface. Concave spherical refracting surface. Concave spherical refracting surface. See here. Now let us define convex spherical refracting surface and concave spherical refracting surface. Look at here. Convex spherical refracting surface mean the spherical surface which convex. This is convex. The convex is towards the rarer medium. I mean, the spherical refracting surface in which its convex is toward rarer medium, that we are calling convex spherical refracting surface. Similarly, the spherical surface which concave, this part I can call concave. The spherical refracting surface which concave is towards the rarer medium, that we are calling concave spherical refracting surface. Two types of spherical refracting surface available. But both for convex spherical and concave spherical refracting surface, we need to define some basic terms. Basic terms are, first we are calling pole. Pole means the center part of spherical refracting surface, that I can call pole. Center part of spherical refracting surface we are calling pole. Both for convex and concave spherical refracting surface. Later on we define one more term, that we are calling principal axis. The imaginary line joining through pole, that we are calling principal axis. How this is for this surface? If we join this line, this becomes what? Principal axis. Or if we take for this surface, if we join imaginary line, this becomes what? Principal axis. One more term we can define, that we are calling center of curvature. For both convex and concave, I can take this is center part, or this one you can call center part. This center part, center of curvature is the center of sphere. Center of curvature is the center of sphere of which spherical surface forms a part. I mean the center of the sphere in which the spherical refracting surface forms a part. This we are calling center of curvature. This also becomes center of curvature. Later on, we should define one more term, that we are calling what? Radius of curvature. The distance between pole and center of curvature, that becomes radius of curvature. Similarly here also, distance between pole and center of curvature is called as radius of curvature. Are you following? This is one thing. And we should define again object distance and image distance. How it is? Let us consider the object situated on principal axis. Let us represent by O. The ray of light incident and get refract. Wherever the ray of light meeting, that point we are calling image, and this we are calling object. This is pole. Distance between pole and object is called as object distance. Distance between pole and image, what we are calling this? Image distance. Right. Similar here also. Let us take the ray of light incident. Let us take, it is nothing but the pole, object available some other point, ray of light incident. So after incident, the ray of light can refract like this. This is nothing but the image. Again, distance between pole and object, what we are calling this? Object distance U. Distance between pole and image, what we are calling this? Image distance V. But we need relation between object distance, image distance, radius of curvature and refractive index of the medium. That is refraction through spherical surface. Refraction through spherical surface gives the meaning of relation between object distance, image distance, refractive index and radius of curvature. That we'll see. Before that, we need to some assumptions during spherical refracting surface. Let us take one assumptions. What are assumptions initially? So here, whatever angle of incident, whatever angle of refraction, so those are assumed to be very, very small. This is one assumption. And second assumption is the ray of light which is passing through principal axis, the ray of light never deviated. That is second assumption. One more assumption. Whatever aperture available for a spherical refracting surface, and that aperture is very, very smaller. And one more assumption you can take, the object which is always lying on a principal axis. This is one more assumption. And what are sign conventions we are using during refraction? Whatever sign conventions we used during reflection of the light, same sign convention we will take. First sign convention is the distance, all distance are measured from pole. All distance are measured from pole. Second one, along the direction of incident ray, all distance are taken to be positive. Opposite to direction of incident ray, all distance are taken to be negative. And the distance measured upward perpendicular to principal axis taken to be positive, distance measured downward perpendicular to principal axis taken to be negative. Remember this point. By taking all this point, let us take what is the relation between object distance, image distance, radius of curvature and refractive index of the medium. That we'll see now. Let us see. Now this relation you can achieve either by taking convex spherical refracting surface and concave spherical refracting surface. If we get one of the surface, then easily you can get for under surface. Let us see. For my convenience, I will take convex spherical refracting surface. Look at me. Now shall I discuss? Simply I will take convex spherical refracting surface through which the ray of light incident and get refracted. Very simple. Listen to me. Simply I will take, this is nothing but one spherical refracting surface. This I can call spherical refracting surface. say this surface becomes convex spherical refracting surface. Right or wrong? Now consider this convex spherical refracting surface has refractive index n2 and this radar medium has refractive index what value? n1. We know that the center part of spherical refracting surface is called as pole. This we are calling pole. Center part simply we are calling pole, right? The imaginary line, see here, for my convenience I will take here, look at me, simply I will take like this. This is convex spherical refracting surface. The center part I can call pole, right? Imaginary line joining through pole, what are calling this? Principal axis. Are you following me? Now, we know that consider the object which is situated on principal axis. Where the object situated? Object situated on principal axis. Let us, my convenience I will take here. Let us consider object is situated here. Oh. Now, the ray of light incident on spherical refracting surface and get refract. How this is? Let us consider this nothing but one ray of light incident at point A. After incident, we know that perpendicular line drawn at point of incident we are calling normal. Say normal drawn from center of curvature C. After incident, the ray of light must refract in this direction and meets at point I. Right? How this is? This is one more ray of light OA incident at point A and get refracted along the direction of A and meets at point I. Now, one more ray of light that is passes through principal axis, this ray of light never deviated. This is the assumption. Right? But we know that angle between incident ray normal, we are calling angle of incident. Angle between refracted ray normal, what are calling this? Angle of refraction. Remember this point? Now let us use sign conventions. The distance between pole and object, what are calling this? Object distance U. Distance between pole and image is called as image distance V. Similarly, distance between pole and center of curvature, what I can call this is radius of curvature R, capital R. Right. Now listen to me. The ray of light travels from radar medium to denser medium at an angle of incident I, at an angle of refraction R. Let us apply Snell's law of refraction. What Snell's law of refraction says? See here, the ratio of sine of angle of incident. Ratio of sine of angle of incident to sine of angle of refraction is constant. Refractive index of second medium with respect to first medium. Refractive index of second medium with respect to first medium. Then ratio of sine of angle of incident to sine of angle of refraction is equal to n2 divided by n1. Or else simply I can take n1 sine I is equal to n2 sine R. But what is the assumption? Whatever angle of incident, whatever angle of refraction, so those are assumed to be very, very smaller. See here, theta is very, very smaller, sine theta nearly equal to theta. Then sine I nearly becomes what value I? Again sine R nearly becomes what value R? Let us call this is equation number 1. For my convenience I will take. Look at me. This one I can take equation number 1. See here. But I should define object distance, image distance by taking sign conventions. Along the direction of incident ray, all distance are taken to be positive. Opposite to direction of incident ray, all distance are taken to be negative. Right? See here. Distance between pole and object is called as object distance. Then shall I take this PO is equal to what value? Minus U, because it is opposite to direction of incident ray. Distance between pole and center of curvature, that is PC. PC is equal to radius of curvature. Look at me. PC is equal to radius of curvature. Distance between pole and image, Pi, it is called as image distance, represented by V. Right things? But now for geometry, I should draw one more perpendicular line. Look at me. Simply I will draw AN perpendicular to principal axis. AN perpendicular to principal axis for geometry. Then in the figure, this N point is very closer to P point. N point is very closer to P point. So that how to take this P point is very closer to N point. Directly I can take this P is equal to N from the figure. It is assumption. Now I need to find the value of I and value of R. To find the value of I and value of R, look at here, so many triangles are there. In the triangle OAN, here one angle looks like this angle, shall I take it is alpha? Right thing? One more triangle looks like ANI looks like one more triangle. In this triangle, I can take one more angle, that angle taken as beta. Similarly, one more triangle looks like ANC, one more triangle. In this triangle, this is gamma. Right. I need to find the value of I and value of R. To find the value of I R, again I need alpha, beta and gamma. See here. In this figure, what we know? This alpha and gamma are looks like interior angles. Looks like interior angle. And what is I angle of incident? That is looks like exterior angle. From geometry, what we know? Angle of incident, sum of exterior angle is equal to sum of interior angle. Exterior angle. Exterior angle mean I. I is equal to how much? I is equal to alpha plus gamma. I can take it is equation number 2. One more triangle. See here. Look at in the figure. In the figure, this R and beta looks like interior angle. What is gamma? Gamma looks like exterior angle. Sum of exterior angle is equal to sum of interior angle. Again, from geometry, what we know? Gamma is equal to R plus beta. Or what is R? R is equal to gamma minus beta. Let us call this is equation number 3. Right. See here. Now in the figure, I need again alpha, beta and gamma. To find alpha, beta and gamma, look at me here. See here, shall I take alpha, beta and gamma? In the figure, one more triangle looks like. See here. One more triangle looks like. Which is the triangle? I can take AOAN looks like R. OAN looks like one triangle. See here. In the figure, one triangle looks like, which is triangle tan alpha. See here. Triangle OAN. OAN looks like one triangle. In this triangle, I will take tan alpha. Tan alpha. What is tan alpha? See here. Tan alpha is equal to how much? Tan alpha is equal to opposite by adjacent. Shall I write here? Tan alpha I will take. Tan alpha is equal to AN divided by ON. AN divided by what value? ON. It is one triangle. But again, what we know? P point is very closer to N point. P point is very closer to N point. Wherever N, that I will take P value. Then again from this, tan alpha is equal to what value? PA divided by PO. Theta is very smaller. Tan theta nearly equal to theta. Tan alpha nearly equal to alpha. Alpha is equal to how much? That is PA divided by PO. Remember this alpha value. This alpha value shall I take it is equation number 4 now for my convenience. I think. Then one more triangle is there. Which is triangle? I can take AIN looks like one triangle. AIN. Triangle which is triangle? Triangle AIN looks like one triangle. In this triangle, I will take tan beta. See here. Tan beta I will take. Tan beta. What is tan beta from this triangle? Tan beta is equal to what? Opposite by adjacent. Opposite is equal to AN. Adjacent is equal to what value? NI. Again from figure what we know? P point is very closer to N point. So that again tan beta I will take, theta very smaller I will take, then directly tan beta is equal to beta, then PA divided by PI. For my convenience I will take. Let us call this is equation number 5. One more triangle, gamma is there. Which is triangle? Triangle I will take ACN, looks like one triangle. ACN looks like one triangle. In this triangle I will take tan gamma. Tan gamma. What is tan gamma? Opposite by adjacent. Opposite is equal to AN and adjacent is equal to what value? NC. Again N point is very closer to P point. So that again theta very smaller, tan theta nearly equal to theta, then gamma is equal to much? Gamma is equal to PA divided by PC. So this is equation number 6. Right? Look at me. We got like this. Now put value of alpha, beta and gamma in equation 2 and equation 3. See here, what we get done directly? Look at me. I is equal to how much? Alpha plus gamma. Alpha is this value. Alpha plus gamma. PA divided by PO. Gamma is how much? PA divided by PC. Let us call this is equation number 7. Equation number 7. Then look at me, equation 3. R is equal to R gamma. Gamma this much. That is PA divided by PC minus beta. Where is beta? PA divided by PI. PA divided by PI. Let us take equation number 8. Right. Now put equation 7 and equation 8 in equation 1. Then we get the relation between object distance, semi distance or radius of curvature along with refractive index. See here. What you got? Equation 1. N1 is there. N1 keep it up same. I value. I value is from where? Equation 7. That is PA divided by PO. PA divided by PO plus PA divided by PC. Right thing? PA divided by PC is equal to N2 R. R is from where? Equation 8. PA divided by PC minus PA divided by PI. Right thing? Look at me here, LHS and RHS. In LHS and RHS, what is common? PA is common on both sides, so that P can be removed. Then what you got? N1 multiply inside. N1 divided by PO plus N1 divided by PC is equal to N2 divided by PC minus N2 divided by PI. Now let us use sign conventions. PO is equal to minus U, PC is equal to R, PI is equal to P. How to put that? N1 divided by minus U plus N1 divided by R is equal to N2 divided by R minus N2 divided by V. Right thing? Just rearrange these equations. Rearrange mean minus and this V bring this side and this N1 bring this side. What you got? Minus N1 divided by U plus N2 divided by V is equal to N2 divided by R minus N1 divided by R. Here R is common, then what you got? Minus N1 divided by U plus N2 divided by V. N2 divided by V is equal to N2 minus N1 divided by R. This is refraction through spherical surface in case of convex spherical refracting surface. Look at me. U represent object distance, V represent image distance, R represent radius of curvature, N1 and N2 represent refractive index of radar medium and refractive index of denser medium. Let us consider this second called radar medium. Radar medium, and what about this medium? This medium I can call denser medium. Radar medium and what value? Denser medium. Well, it is when surface is convex spherical refracting surface, then we are using this relation. But wherever surface is concave spherical refracting surface, concave mean how it is? Look at it. If the case, surface must be like this. Surface must be concave spherical refracting surface like this. This second called take what? This second take pole, right? How the object is there? This second take object, right? And ray of light can refract it like this way. This is nothing but pole. And this is the object distance. What about the semi distance? Though this is refractive index n2 and whatever refractive index n1. Ray of light travels from denser to rarer. In this case, what happened? Ray of light travels from rarer to denser. Then for concave spherical refracting surface, how to write this value? This equation. Simply this equation can replace by changing refractive index. Here n1 minus n1 by u, n2 by v is equal to n2 minus n1 divided by r. Now, for this surface, simply exchange the refractive index. Refractive index means wherever n1 I will put n2, that is n2 divided by u plus n1 divided by v is equal to n1 minus n2 divided by r. This is the relation I can use. For convex spherical refracting surface must be like this. For concave spherical refracting surface taken must be like this. So this is refraction through convex spherical refracting surface and concave spherical refracting surface. The remaining session on spherical refracting surface that we'll see in the next session. Thank you guys.